Welcome to the first exam in my quantum mechanics lecture. Now, I may be making more exams if you're interested, so if you enjoy this or find it useful, please let me know in the comments so that, because it's a lot of work to put together these kind of exams, solve them, and then put the solution out for you. So if you enjoy it, please let me know in the comments or in the Discord server. The link is in the description, or wherever we want. So there's going to be 3 questions in this exam, and you have 2 hours to solve them. The topics are going to go from the very beginning of the Quantum Mechanics 1 course, right? So just basic Schrödinger equation normalization and understanding what it means, up until the beginning of the harmonic oscillator. So no oscillator in this test or this exam, but just before it, right? So it's going to cover the delta potential, as you can see, and it's also going to be working or covering the infinite square well. Okay, so as I mentioned, you have 2 hours. I'm going to show you here the questions so you can pause and read them. I'm also going to show them later as I'm working on them. And this is the 3rd one and the appropriate graph for part 2. So that is all the information that you need. I encourage you, strongly encourage you, that you pause the video, try to solve it yourself, time yourself, right? Try to do it and then come back. That is the best way to learn, right? This is an exam. Don't take this as any other video where no. Try to solve it, take the time, and then come back, right? So this is what a quantum mechanics exam in college may look like for you. So take it as it is, take it seriously, right? And yeah, so I'm just going to go ahead and start solving it. So I hope you paused, as now the solutions will start coming in. So here we have problem 1. It says a particle of mass m is described at a certain moment by the unnormalized wave function phi x is a times e to the minus a different a, small a, absolute value of x, where small a is positive. So our first task is to find big A, the normalization constant, and in B we want to find the length of the interval L around the origin, which means the region between minus L to L, right, where x is between minus L and L, where the probability of finding the particle is 0.4. Okay, so this, again, pause the video, try it yourself, and then come back. So here, this is basically testing how much you understand about what normalizing means. So what we have to do here is simply, well, we want to find A, normalize. So we're going to say, well, the probability density squared here of our function is going to be 1. So we're going to integrate through the entirety of space our function, right? Phi x squared dx. That's what we have to do for part A. Maybe let me write here that this is part A so that it is very clear. All right, and well, let's work on this. So now we have the integral between minus infinity and infinity. This thing right here is going to be phi conjugate of x, phi. However, our phi is real, so the conjugate doesn't really do anything, but in some situations it could. So it's important to always keep in mind that it is supposed to be that way. So our function is a e to the that, so we are simply going to have our function squared. So we get a squared e to the minus 2a, right? It's the exponent squared. You simply get a 2 in the exponent, minus 2a absolute value of x. Now, I think one of the most challenging things in this problem is knowing how to deal with an absolute value in the exponent. And the way to do that is to remember, well, what is the absolute value? Well, the absolute value of x is going to be minus x if x is negative, right? Smaller than 0. And it is going to be, absolute value of x, this is going to be x, maybe let's put the if x is positive. So doing that, we are simply going to separate our integral. Now you could also say, well, this is an even function. That's also something you could say, and I will explain it in a moment. So this is 1 equal 2, and now we have the integral separated. So the negative numbers from minus infinity to 0, and now we have a squared e to the minus 2a minus x dx. And now we have plus, and now we integrate over the positive numbers. and this would be a squared e to the minus 2ax dx. All right. And here we can do a few things. So of course here the minus signs would cancel out, and we have integral from minus infinity to 0 of a squared e to the minus positive, so 2ax dx, plus this thing which has not changed at all. Now we can solve this. You can either just integrate right away. It's not a difficult integral, so integrating twice is not much work. But I also want to show you that you could, just play around with the properties. I like trying to get you guys used to this sort of thing. So you could here say, well, 1 is going to be equal to, and you can now flip the limits of integration, basically. So we are going to integrate from 0 to minus infinity, and we put a minus in front, and then we have everything else, 2ax dx plus that same thing. And now we can do a little bit of a change of variables where we let x go to minus x, right? And that means that our dx goes to minus dx. So before, in our limits, when x used to be 0, it's now going to be, well, still 0. But now when x used to be minus infinity, it's now going to be infinity. Now, this is not something you have to do, but I just like to do it so that you can see 1 is equal to, and now, well, this minus sign is going to cancel out with a minus sign that comes from the new dx. So we get a positive. The integral now goes from 0 to infinity. Then we have a squared e to the minus 2ax dx plus that same thing. But if you notice, now we have the same thing twice, right? So that thing is exactly the same that we just found. So we simply have 2 times integral from 0 to infinity, a squared e to the minus 2ax dx. And another way that you could have gotten to this is if you had just seen, well, I have an even function. And when you have an even function, then you simply take, your result is twice one of the halves. So you could have written integral from 0 to infinity, 2 times a squared e to the minus 2ax dx. And since you're now only in the positive numbers, you keep the positive x. So you could have done that as well. It's exactly the same. You also could have just gone for the brute force method, where you integrate this expression and don't bother about the whole changing signs thing. It's all the same. All of those forms are valid. The important thing is that now we get to this expression and we integrate. So we have 1 is equal to 2 times a squared. We take it out of the integral. It doesn't depend on x, so no worries. And now we integrate the exponent. So we get 1 over minus 2a. And now we get e to the minus 2ax evaluated between 0 and infinity. So this would be, the 2's cancel out. We have minus a squared over a. And now we have this evaluated at infinity, leaves that as 0, right? Minus e evaluated at, or e to the minus 2ax evaluated at 0 is going to be 1. So we get minus 1. So in the end, this thing is a squared over a, and we know that it has to be equal to 1. Therefore, our a is simply the square root of a. So let's now do part B. So we want to find the length L of the interval around the origin, well, that is, the region minus L, smaller than x, smaller than L, where the probability of finding the particle is 0.4. So here, all that we need to do is, well, let's say in general first, the probability of finding our particle between minus L and L is going to be the integral between minus L and L of our probability density. So that's going to be phi of x squared, and of course dx. So let's plug in what we know about our function. So this is minus L to L, a squared e to the minus 2a absolute value of x dx. Okay, let me zoom in. So now we know this is an even function, like I just explained. So this is 2 integral from 0 to L. You could also just separate it and integrate twice, or do any of the other ways of solving this. a squared we just found is a, right? A is square root of little a, so big A squared is small a. All right, and then we have e to the minus 2ax. We can drop the absolute value since we are now only dealing with positive numbers. Dx. Okay, so here we integrate, we have 2a, 1 over minus 2a, and now we have the actual value, so this is e to the minus 2ax evaluated between 0 and L. So here these things cancel out, we get a minus sign. And then we have e to the minus 2al minus e evaluated at 0, which is going to be 1. So with a minus sign, I use different parentheses, there we go. With a minus sign, we get that this probability is 1 minus e to the minus 2al. Now always, whenever you get to a result, try to figure out if this makes sense or not. So in our case, the larger L is, the bigger the probability that our particle is going to be in that interval. And that makes sense. If L goes to infinity, we are covering the entirety of space. And therefore, we expect that the probability of finding the particle somewhere in any part of space is going to be 1. And the smaller L is, then the probability is going to be smaller and smaller. So that makes a lot of sense. So that's good. And this was in general, right? So probability in general. Now let's go for our case. So in our case, we wanted to know what the length L is so that our probability is 0.4. So we plug in 0.4 for the probability, basically 40%. And then you have 1 minus e to the minus 2al. And now we solve this as best as we can. Of course, we don't really know what a is, but we're going to leave the answer in terms of a. So here we have, let's put the e to the right hand. So we have e to the 2al. This is equal to 0.6. We can take the natural log on both sides, right? So natural log, so that we have 2al is equal to the natural log of 0.6. And finally, we get that L is going to be the natural log of 0.6 divided by 2a. So this is the answer. If we know what a is, right, which is the only thing that we don't know about the function, we know exactly what this length L is supposed to be. All right, so now for problem 2, it says, consider a particle subjected to the following one-dimensional potential. So the potential is what we can see here on the right-hand side. If x is smaller than 0, we have an infinite potential. Between 0 and x0, we have no potential. And then at x0, we have an infinite potential, the delta potential, right? And then we have 0 again. So this is the drawing of the situation. And the potential itself of the delta looks like this, right? Minus a delta of x minus x0, right? Of course, located at x equals x0, right? Okay, now we want to write the time-independent Schrödinger equation in both regions of interest. Why is the region x smaller than 0 irrelevant? That's part A. Right, so that's part by part. And notice this is going to guide you through the solution. So this is hopefully going to be helpful. B is going to be restrict to the case of bound state, which is E smaller than 0. And that's always going to be the case in a quantum mechanics 1 course. You're not really going to be dealing with scattering, which is the other case when it's not a bound state. You're not going to deal with that in this kind of course. Solve the Schrödinger equation in both regions, impose the appropriate boundary conditions at the origin and for x going to infinity, right? We have done this many times throughout my courses. Write down the boundary conditions for the wave function at the point where it crosses the delta potential, obtain a transcendental equation whose solution allows you to find the possible values of E, provide a graphical solution of the problem. It is very common that you can't actually find the solution by solving an equation, but rather you have to go to like numerical or graphical methods. So that's what we will do, like we did again when we are going through the course. And we're going to establish the condition that fixes the remaining global constant. Okay, so I think this is probably the hardest problem in the exam, at least in my opinion. So let's go step by step. So problem 2a says, write the time-independent Schrödinger equation in both regions of interest, right? So this is going to be region 1, this is going to be region 2. All right, so in region 1, we have, so this is going to be second derivative of psi 1 with respect to x squared. We have minus h bar squared divided by 2m. Our potential is 0, so we have plus v times the potential, but that is 0. This is equal to e psi. Psi 1, of course. Let's make it very clear where we are. And I guess we could write this as a function of x, but usually I'm too lazy to do that. In region 2, we have, well, the same thing basically, minus h bar squared, 2m del squared psi 2 of x. I'm writing this as a partial derivative mainly because I'm so used to, but I guess we are like in a one dimension, so I'm just gonna be very one-dimensional here. All right, and this is equal to e psi 2 of x. Okay, so with this, we basically have part A ready. We just need to answer, why is the region x smaller than 0 irrelevant? Well, because there's an infinite potential, right? An infinite potential means that our wave function is 0, right? We have also talked about that a lot during the course. If we cannot really have a state if there's an infinite potential, it's just not possible. So yes, that's part A. Now let's go for part B. Restricting to the case of bound state, right? E smaller than 0, solve the Schrödinger equation in both regions. So in part B, it says restrict to the case of bound states, which means E smaller than 0, solve the Schrödinger equation in both regions, impose the appropriate boundary conditions at the origin, and for x going to infinity. Okay, so now we basically want to solve the equations that we just wrote down. So let's begin with region 1. All right, so in this region, what we want to solve is now minus h bar squared over 2m, second spatial derivative, is equal to e psi 1. And here, how do we solve this? Well, I have a very, very favorite method for solving this sort of differential equation. So I'm going to, of course, isolate our derivative. So we have d squared psi 1 dx squared. This is equal to minus 2me over h bar squared times psi 1. All right. And with this, we want to define our constant k, right? Or sometimes it's k or l, or depending on how many regions you may have. So how do we choose, right? We have k is equal to 2, or rather k squared, 2me over h bar squared, like it usually is. But do we include the minus sign or not? Now, the way to know that is to keep in mind we are in the case where the energy is negative. And we do not want there to be a square root inside of k, or a negative inside the square root. We know that k is going to be the square root of whatever we have inside. So for that reason, since e is negative, right now this would be a negative quantity. So the minus sign should be included so that we have a real number in here, or a positive number, and we get a real amount in the end. So for that reason, we do include the minus sign, and that means that we end up getting, instead of this thing, we have k squared. All right, what is the next step? Now, there's a ton of ways of solving this. My favorite way is to do it like this. I write everything to the left side. I guess you could do it to the right, doesn't matter. dx squared, and I factor out my psi's. So I have this thing minus k squared, all of this acting on psi 1. And this is equal to 0. And now we write this as ddx plus k times ddx minus k. Psi 1 equals 0, right? This is nothing illegal. We're just doing simple algebra. Now for this thing to be 0, either this acting on psi is 0, or this acting on psi is 0. So now we get two equations. We're going to get that dx of psi 1 plus k psi is equal to 0, or we're going to get from this one that dx psi 1 minus k psi 1, I guess I should specify this here as well, is equal to 0. So here we can very, very quickly solve these equations. We can separate the variables so that we get that d psi 1 over psi is equal to, so what I did is I put this to the side. Maybe I shouldn't have skipped that step just to make this very clear. So let me not skip a step. So this is dx equal to minus k psi 1. And from here, we do separation of variables. So we have d psi 1 dx. Sorry, I was supposed to do separation, so I guess I should have written this. This is equal to minus k dx. Now let me separate this. And now we integrate this, right? We integrate. And what we are going to end up getting is that we have the natural log of psi 1, which is going to be equal to minus kx plus, some constant of integration. And now we exponentiate all of this so that we end up getting psi 1, which is going to be some constant a e to the minus kx. Now this a is simply e to the c, right? Because that thing is in principle e to the c, e to the minus kx, but we just renamed e to the c a, because e to any constant is still any constant. So that's what happened. So similarly, we can solve this thing, and the only difference is this minus sign. So the only difference is that instead of having this minus, we are going to end up having a plus. So we get some other constant and then e to the plus kx. So this is the solution for our region 1. Now in region 2, so maybe let's write it here off to the side. So in region 2, well, actually, we have the exact same equation. So we're going to have the exact same possible solutions, right? It's exactly the same solutions. So we have psi 2, this is going to be, let's call it c, e to the minus kx plus d e to the kx, right? So in principle, those are the solutions as well. So those are our solutions for both regions. Now let's impose boundary conditions, right? It's basically the same procedure that we do in every Schrödinger equation problem. So what are the boundary conditions? So let me maybe copy our solutions down here and work from there. Okay, as I said, let's now impose boundary conditions. So impose. All right. So what are the boundary conditions? Well, for region 1, we have that psi 1 evaluated at 0, right, should be 0. Why? Because, well, we have this infinite potential here. So the wave function has to die when it gets to the infinite potential. For psi 2, we need that as x goes to infinity, we want the wave function to be 0. Otherwise, it's going to be non-normalizable. So for that reason, we need d to be equal to 0. Otherwise, we cannot normalize this, and yeah, we can't really go anywhere. All right, so with regards to this, to region 1, we can go a little bit further, right? Actually plug this in. So we get 0 is equal to a e to the minus 0, 1, plus b e to the 0, 1. So we get a plus b. So this means a is equal to b, or rather minus b. So now let's plug these conditions in and get our final wave functions. So this would be here, a is equal to minus b. Now we can plug in a equals minus b or b equals minus a, either one of them. Now because of the way this is, we have e to the kx, e to the minus kx. When you have that, your mind should always be adjacent to hyperbolic sines and maybe cosines. Since we have a minus, and I know that the hyperbolic sine of, well, let's say x in general, so of x, this is e to the x minus e to the minus x over 2, right? So for that reason, I would maybe like the minus to be adjacent to the negative exponent, and that way I can simplify my notation. Now, if you don't know this, it doesn't really matter. You can carry on with your exponents. The only reason why I like to do this whole hyperbolic sine thing is because it makes notation much cleaner and easier to work with. If you don't think about this, that's fine. You can still get to a correct version of the result. So don't worry if you hadn't thought of that, or if you're like, hey, but why are you doing that? Simply because it looks better. So for that reason, I will write a is equal to minus b, right? So that will make this be minus b e to the minus kx plus b e to the kx. So let's now write this as 2 divided by 2, right? We are multiplying by 1. And with this, we also factor out b, so we end up getting 2, that 2 looks weird, 2b, and the thing inside is now e to the kx, I'm rearranging, minus e to the minus kx over 2, and that thing is simply, well, that's going to be, we can rename this, but 2 times any constant, that's just another constant. So we can call this e if we want, or we can call this like a hat or b hat, doesn't matter, right? Or a tilde, whatever. And what we have inside is our hyperbolic sine of kx. All right, so you can see that's a much cleaner notation. Now, with regards to region 2, we simply get c e to the minus kx. And that's it. Now that we have that, we want to go for the other boundary conditions, right? Part C. This time, we want to discuss now what happens around the delta potential, right? We want to start putting everything together. So the way to do this, or to do it in this kind of problem, right, there's usually not much of an issue in terms of the wave function, right? What we know is that our wave function, psi1, evaluated at our potential here, is going to have to be the same as the potential from region 2 evaluated at that point. There has to be continuity, right? What this means is that if we have a wave function somewhere over here, right, something like this, and it gets to the potential, it can't magically jump and start over here. We can't have one of these jumps, right? So that's very important. That's what we are saying here. And now with regards, I guess I should write that this is part C now. And now with regards to the derivative, that part is where things get complicated in the sense that it is hard to think about this if you haven't learned it, right? But as I've mentioned, this is what you have to do basically in every single like delta potential problem. So what we want to do is the following. So we write down the Schrödinger equation, minus h bar over 2 to m. We have our little psi, which is 2 times derived with respect to x. We have our potential times our psi, and then we have e psi, right? Nothing crazy. And what we do is that we integrate the entire equation from x0 minus epsilon to x0 plus epsilon, right? So we're going to be integrating from basically very, very close. So we're going to start off somewhere over here, right? This is x0 minus epsilon, and we integrate to x0 plus epsilon, and then we make epsilon go to 0. So that's what's going to be happening here. All right. So here, now this is again something that we have done extensively when we were covering this. The energy part will, well, actually, maybe let's write it entirely before I start saying what things are going to be. So this is minus h bar squared over 2m integral x0 minus epsilon x0 plus epsilon. And now we have d squared psi dx squared dx. And we have plus, again, integral x0 minus epsilon, x0 plus epsilon, our potential, our function, which I guess I'm going to write that it depends on x, just so that you don't make a mistake and maybe take it out of the integral thinking it doesn't. This is equal to the energy, integral x0 minus epsilon, x0 plus epsilon and psi of x dx. Now here we can take the energy out, and this is simply going to be 0, right? It's going to be an infinitely shrinking tiny sliver of the function, which is now going to go to 0 as epsilon goes to 0, right? So this is 0 as epsilon goes to 0. So that part is not an issue. What we have here on the left side, well, we are taking the integral of a derivative. So fundamental theorem of calculus tells us that this is going to be simply, well, what is inside. So we had two derivatives, we are left with one, psi of x dx evaluated at x0 plus epsilon minus that same thing evaluated at x0 minus epsilon. All right, and now keep in mind, this is in region 2, right? We are to the right of x0. So this here is going to be wave function 2, and this here is going to be wave function 1. All right, I used more space than I wanted, so I need to move this. And now I have plus, and we have the integral of the potential. So this is going to be integral x0 minus epsilon, x0 plus epsilon, and now we have minus a delta of x minus x0 times our wave function dx is equal to 0. Okay, and now we can take the minus a outside, so minus a, we can just take it outside. And what is this thing? The integral of the delta function. You're summing over something that is 0 everywhere except at x0. So this integral is simply our wave function evaluated at the point where it is not 0. So that is what it is. I think this is what we were looking for. Let me go back to see exactly what I was asking for. So write down the boundary conditions for the wave function at the point where it crosses the delta potential. All right, I think I went one step further, but it's fine because we are now going to continue this in part D. So part D, now obtain a transcendental equation whose solution allows you to find the possible values of E, the energy, and provide a graphical solution of the problem. So what we basically wanted to do, by the way, last time, I think up to here is where I would consider C to be correct. It's fine if you go a step further. It is a little bit ambiguous there. Okay, so before we move to part D, maybe let's take this little expression here, right? The fact that our wave function from region 1 at the boundary with region 2, well, they have to be equal. So we know that the wave function at region 1, this is simply a hat sinh kx0, and this thing is going to be c e to the k or minus kx0. So from here we can easily find c. You could solve for a hat as well, doesn't really matter. I think that doing it like this is a bit cleaner, but doesn't matter. So this is a hat sinh kx0 e to the minus kx0, or plus now, right? We have to take it as a plus as it goes to the other side. Now notice that we still have, so we got rid of c, but we still have one more constant, which is a hat, and that is the one that should be found by normalization. And that's, well, going to be the final part of the problem, and it's not as easy as one might like. So this is what we wanted for part C. So in part D, I mean, the boundary, to be honest, between C and D is a little bit fuzzy. So in part D, we want to actually find the transcendental equation whose solution allows you to find the possible values of E. So we don't actually have to find the values itself, just the equation that gives you the values, and provide a graphical solution of the problem. So that is, again, very common for these sorts of problems. So let's go now, part D. So what we want to do is, well, continue working with what we had right here. So plug in our stuff. So this would be minus h bar squared over 2m. And now we take the derivative of the wave function from region 2, right? what was the wave function from region 2? Well, that is c e to the minus kx. So we get a minus k c e to the minus kx, but the x is now going to be evaluated at x0. We don't care about the epsilon anymore. It can go to 0. The importance of the epsilon was letting us know which wave function was where, right? For plus epsilon, we had psi2. For minus epsilon, we had psi1. All right, so we have minus k c e to the minus kx0. And then we get minus the derivative of our other function, which was the hyperbolic sine. So we get the hyperbolic cosine of kx0. We still have our little a hat, and we get a k from this derivative. And then we can put this to the right. So this is equal to a psi of x0. Now that psi of x0 can be any of the two because they are both equal in this limit. Now, I'm going to wait before I choose one because I like to choose one when I know which is going to make things easier for me. So there's no need to commit right away and plug one in. I'm going to wait and see what's best. Okay, so I can now take the minus sign and the k out, and I also want to plug in the value that I just found for c. So I get h bar squared over 2m factor k. And now let's plug in the value that I just found for c. So that is a hat. So that is a hat hyperbolic sine of kx0 times e to the positive kx0 e to the minus kx0. And now we continue normally. So then we have plus, right? We took the minus signs out, a hat cos kx0, and all of this is now going to be equal to a psi of x0. Okay, so with this, we can take the hat here, the a hat outside a little bit. Right, so this would be h bar squared 2m k a hat. The exponents will cancel out, so we get hyperbolic sine of kx0 plus the hyperbolic cosine of kx0. And now to the right side, I'm going to choose to plug in my wave function from region 1, because that way the a hat is going to cancel out. All right, so I'm going to have a hat hyperbolic sine of kx0. So now I can divide. So I can do a lot of things. Let me multiply by 2m divided by h bar squared k. That way I'm going to get rid of these things. And I'm also going to divide by a hat and the hyperbolic sine of kx0. Okay, so let me do that. So when I do that, all of this is now gone. So I have here 1 plus hyperbolic cosine of kx0 divided by the hyperbolic sine of kx0. And what do we have here? Now this part will be 2ma over h bar squared k. And we have, well, that's it. There's nothing else there. Okay, now let me plug in what the hyperbolic cosine and sine are. Right, so I'm going to have this as 1 plus, and this is e to the kx0 plus e to the minus kx0 divided by e to the kx0 minus e to the minus kx0. Each one of them is divided by 2, but since one is divided and the other one as well, they are inverted, those two cancel each other out, right? We would have a 2 here and a 2 here, so they cancel each other. Okay, and this is equal to 2ma over h bar squared k. Good. Now let's take common denominator over here, right? So this would be e kx0 minus e to the minus kx0. And then we have plus e to the kx0 plus e to the minus kx0. Did I do like an additional step? Possibly. Doesn't matter. We'll get there. E to the kx0 minus e to the minus kx0. And well, this is equal to the same thing on the right-hand side. We haven't really touched that at all. Okay, so now here we have that this and this cancel out. So we have 2 e to the kx0 divided by e to the kx0 minus e to the minus kx0 is equal to 2ma. We're almost there, I promise. And with this, we now multiply both sides by e to the minus kx0. So we end up getting 2 divided by 1 minus, and this would be e to the minus 2kx0. And again, equal to this same thing here. But now we can cancel out this 2 with this 2, and we can also flip this entire thing. So everything to the minus 1. That way, we get 1 minus e to the minus 2kx0 is equal to h bar squared k divided by ma. And as I promised, this is what we were looking for. Why? This is the transcendental equation. We can now plot, right, the value of our function in terms of k, well, and the value of k. So 1 minus e to the minus 2kx0 will have a maximum value of 1, right? And it starts at 0 when, let's see, when k is 0, right? So when k is 0, we have e to the 0, so our function is 0. So we start over here. Maybe let's use a different color. And then as k grows, this thing is also going to be growing and growing. So it is something like this. And then we have this, which is simply a straight line with a slope of h bar squared over ma. So it's simply a straight line. So that means there's one point where they cross. So there is one bound state. And well, you could find the solution here with graphic tools. So there we go. That is the solution for part D. Now, if we go to part E, we want to finally establish the condition that fixes the remaining global constant. Okay, so that is the final part. So how do we do that? Well, normalization, right? Part E is saying, well, we want to normalize. So 1 is equal to the integral from minus infinity to infinity of our, well, function squared, basically. But, well, we have a piecewise wave function, basically. So this is 1 is equal to the integral from 0 to x0 of psi 1 squared plus the integral from x0 to infinity of psi 2 squared. Okay, so with this, well, let's plug in what we have. So this would be a hat squared, and that is the hyperbolic sine squared of kx dx. Sorry, this is not 0 to infinity. That is 0 to x0. Sorry, that's my bad. And then we got plus integral from x0 to infinity. And this thing right here is going to be our, well, our second function, which we said is c, right? C times e to the minus kx, so minus 2kx dx. But we know that c is simply a hat, so squared, times the hyperbolic sine squared, in this case, of kx. And let me double check, is that what it was? So, and then we have e to the kx0. Okay, so it is this thing and then times e to the, I guess we can take it out, so e to the 2kx0. Don't get confused. This is kx. This is kx0. So you can't cancel those out. Okay, so be very careful about that. Okay, so now let's do this, well, step by step. So first of all, here let's, well, of course, take this out of the integral. So a hat squared integral from 0 to x0 sin square, blah, 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 blah. We'll deal with this in a moment. And here we will take everything out. So we have also a hat squared. And then we have, let's keep this order. So e to the 2kx0 hyperbolic sine of kx0. The 0 wasn't really visible there, I guess. I needed to do that a bit more clearly. There we go. And then we have the integral x0. I guess we can solve the integral right away, right? That's not a particularly difficult integral. So that would be 1 over minus 2k e to the minus 2kx evaluated between x0 and infinity. Now, as to the first integral, there are many ways to deal with it. Personally, I kind of like the idea of not working with the trigonometric function, or hyperbolic, sorry, and instead working with exponents. So I would like to have this as the integral from 0 to x0 of e to the kx, there we go, minus e to the minus kx0 squared and divided by 2 squared, which is 4. So I like to do that. Then we have so plus a hat squared e to the 2kx0 hyperbolic sine squared of kx0. And then we have this little factor of minus 2k. And finally, now the integral here. So this at infinity is 0. So we get minus e to the minus 2kx0. All right. And yeah, I don't know why I had that large parentheses there. I guess it wasn't needed at all. So just like this. Okay, let's continue. So now we can work on this integral. So this would be again a hat squared integral from 0 to x0. And here we have e to the 2kx. Then we have the cross term 2 times, so minus 2 times this times this. Oh, by the way, I saw I have an x0 there. My apologies. It's not supposed to be an x0. There's so many zeros, I'm writing them down where they're not supposed to be. That's a regular x. So you multiply those two, they cancel out. All right, so that would be simply minus 2. And then we have plus e to the minus, okay, maybe I should stick to the same color. Plus e to the minus 2kx. Okay, and this is divided by 4. We can take the 4 outside. And now this integral is way easier to solve. Now with regards to the other one, the minus signs cancelled out, the exponents cancelled out, so we have a hat squared hyperbolic sine squared of kx0, and we divide this thing by 2k. Okay, so that is where we are currently. Now, with regards to this one, so we have this little front part, and now we can solve these 3 integrals. So the first one, e to the 2kx, we get 1 over 2k, and then we have e to the 2kx evaluated between 0 and x0. Then we have minus 2x evaluated between 0 and x0. And finally, we have, let's see, this would be minus 1 over 2k e to the minus 2kx evaluated between 0 and x0. And then we have this term, so plus a hat hyperbolic sine squared kx0 divided by 2k. Okay, and now we can, let's see, let's work on this still. So I'm going to change colors again. So 1 is equal to, again, we have this little front factor And in here, we have 1 over 2k factor of e to the 2k x0 minus e to the 0, so minus 1. Then we have minus 2x0, and the other part is 0, so no worries. Then we have minus 1 over 2k factor of e to the minus 2k x0 minus 1. And then we have this other part, so a hat hyperbolic sine squared kx0 divided by 2k. Okay, we're making a lot of progress, so let's continue. So here we have a hat squared over 4. And now let's see, we have minus 1 over 2k e to the minus and this thing. So let's put the exponents together. So we have 1 over 2k factor of e to the 2k x0 minus e to the minus 2k x0. We can let the 2 in here. And this is going to be our beautiful hyperbolic sine of kx0. But there's a 2. So it's 2kx0. Okay, so we have that. And then we have minus 2x0. And then we have still this term and this term, which is going to be 1 over 2k with a negative and positive 1 over 2k. So they cancel each other out. This and this, they cancel out. Okay, so that's a lot of progress that we're making. And this is a hat sinh squared kx0 divided by 2k. Okay, so let's continue. And here we have a hat squared over 4. So let's factor out the a hat squared. So I'm going to put this 1 over 4 in. So we have 1 over 4k, the hyperbolic sine of 2kx0 minus x0 over 2, and then we get plus the hyperbolic sine squared of kx0 divided by 2k. All right, here we're basically done. There's a few more things we can do to make this look a little bit better. So for example, we know that the hyperbolic sine of 2x in general is going to be 2 times the hyperbolic sine times the cosine. So for that reason, we can rewrite this as a hat squared, which is going to be 1 over 4k. And now we have times 2 hyperbolic sine cosine. No, sorry, it's not x. I was just copying that. This is k x0 and cosine k x0 minus x0 over 2. And then we got this plus this thing. Okay, so this 2 and the 4 cancel out partially, right? So this is now a 2. So now we can just factor out a few remaining things. So we can say, okay, so 1 is going to be equal to a hat squared divided by 2k. And then we would have inside, we can factor out the hyperbolic sine kx0. So we have a hyperbolic cosine kx0 plus the hyperbolic sine kx0. And then we have this little term, which is now going to be minus kx0 over 2. So that is as far as we can get. And that is as far as we need to get, at least in terms of the exam. More than this, we need very advanced methods to solve this, and that's way beyond the scope of what we are currently doing. Okay, so let's now get to question 3. So now what we want to do is the following. We say, suppose that at t equals 0, a particle is located on the left side of a one-dimensional box with infinite walls at x equal plus and minus a over 2, right? So some sort of situation like this. So we have an infinite wall, zero potential, infinite wall, right? And we know that this is going to be the function, where the wave function is going to be according to that that we have right there. And a is greater than 0. So the question A is going to be, well, write down the most general form that the wave function will take at an arbitrary time t. And then they ask, will the particle remain localized on the left side of the box or not? Notice, right, at time equals 0, it is perfectly localized, basically, right? It is at square root of 2 over a. Right? It's there, and there is where it is. Part B is if the energy of the particle is measured at t equals 0, what are the probabilities of measuring the ground state energy and the energy of the first excited state? Okay, well, let's get to that. So there's a few things to do. So we want to find the most general form. So that's actually not particularly difficult, right? All that we want to do is say, well, psi of x comma t is going to be psi of x comma t equals 0, but now with the added time dependence, right? E to the minus I E n t over h bar. Keeping in mind, right, the energy for the infinite square well is n squared pi squared h bar squared over 2ma. So that's very important. Now how can we write this overall, right? What is this thing? Overall, right, as you may recall, we can write this function psi of x comma t equals 0. We can write it in terms of, actually, I didn't mean to write it again. We can write it in terms of this sum of coefficients, Cn, and then we have to actually multiply it by these little, I think we call them Fn of x. I think that's what we call them in the video I made about it, just to be consistent. And then we have this e to the minus I e n t over h bar. So this is the most general way to write this. But of course, well, what are these Fn's? Well, we can write these Fn's in the following way. So this, in our case, is going to be square root of 2 over a sine of n pi x over a. This is going to be for even n, so 2, 4, 6, etc. And in the case of odd n's, we're going to have the cosine 2n pi x over a, right? As you may recall, we can separate the solutions here in the case for the infinite square well. So that's what we did. We separate them in even and odd ones. Okay, so now with this in mind, well, I mean, this is kind of it. Now we just need to, well, will the particle remain localized on the left side of the box? No, right? That's the whole point also of the time dependence here. It's going to spread out as time goes on, so it's not going to be localized anymore. In part B, we want to know, well, what are the probabilities of measuring the ground state energy and the energy of the first excited state? Well, that's exactly what these coefficients are for. So the probability that the particle will be in the first energy state is going to be C1 squared. So that is one of the things we want to know. The other one is, well, what is C2 squared? Right? The first and second, or rather the ground state, C1, first excited state, C2. Or I guess it could be Z0, Z1, depending on where you start counting, but the way I defined it, it is this way. Okay, so with this, we can slowly begin. Now the question is, well, what are the Cn's? Because I have this expression over here, I don't really have an expression for the Cn's themselves. Now you can either, from memory, right, remember what it is, and if not, don't worry. So the way to do this is to go back to this little expression. So basically this thing. So keep in mind that psi of x comma t equals 0. This thing is the sum over n of Cn f of n x. And now we can multiply by fm conjugate of x, and we integrate over our entire box. In this case, it would be minus a over 2 to a over 2, but there is nothing on the right half of the box, so we go up to 0, and then there is nothing more, dx. And the whole point of doing this is that, well, now on the right side, we get a little bit of an integral, minus a over 2 to 0, fm conjugate of x dx psi of x comma t equals 0 dx. Oh, sorry. Okay, I didn't see I had the dx. Sorry. Okay, there it is. And then we have sum over our cn's. And now we have integral from minus a over 2 to 0 of fm conjugate x fn of x dx. And what is this? Our solutions are orthonormal, orthogonal and normalized. So if you multiply any two of them, if they are not the same state, you get 0. If they are the same state, you get 1. That means this is the delta Kronecker mn. That means that m and n can only be the same value, otherwise it's 0. So what happens to our sum? It dies. We can only get one value, so we get Cn. And that means every m over here is also an n. You can also choose to stay at m instead, doesn't matter. So with that, we get our little expression, right? So we get that our desired Cn's are going to be integral from minus a over 2 to 0 of fn conjugate x psi x comma t equals 0 dx. Okay, so let's use this. So for C1, right, so we have this expression, blah, 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 blah. Well, C1, for 1, we are at cosine. So this would be square root of 2 over a cosine of n, which is 1, pi x over a. And now we multiply by what our function looks like. Well, we go up, we go up, we go up. And it is simply square root of 2 over a. So a very, very, very simple wave function. So square root of 2 over a dx. Okay, so we get a little factor of 2 over a outside, and we need to integrate the cosine. What is the integral of cosine? Well, sine. So this is sine of pi x over a. We multiply now by, because of the chain rule, a over pi. And we evaluate this between minus a over 2 and 0. So with this, let's put this factor outside. So we get 2 divided by pi. So now we get sine at 0, which is 0. So I guess we get sine of 0, which is 0, minus sine of pi over a times minus a over 2. And, well, the a's cancel out, so we get sine of pi over 2. We can take the minus sign outside. Sine of pi over 2 is 1. So this thing is simply 1. So we get 2 over pi. That means that C1 squared, the probability of finding our particle in state 1, is going to be this thing squared, so 4 over pi squared. That is the first one, but nothing too crazy. Now we go for C2. So C2, this would be now the same thing, but plugging in the second state. So minus a over 2, 0. Now the second state is with sine. So 2 over a, and we have sine of n is now 2. So 2 pi x divided by a, and we multiply by square root of 2a, which is our original state, right? Dx. So again, this is not particularly difficult to do. We get a factor of 2 over a outside. We have to integrate sine. So integrating sine, we get a minus, right? So we get a minus cosine of 2 pi x over a, and we have to multiply by a divided by 2 pi. And we evaluate this between minus a over 2 and 0. Let me move this. So here we have, let's simplify these factors. We get a factor of 1 over pi outside. And then we have, so minus cosine evaluated at 0, we get minus 1. And then we have a factor of minus, but careful, we get minus minus. So now we get plus. The second one, so that would be cosine of 2 pi over a, and this little x is where we plug in minus, but the minus doesn't matter, cosine is even, so we get a over 2. So it is cosine of pi. Cosine of pi is minus 1. So in the end, we get minus 2 over pi. So C2, this is going to, so squared, this is going to be 4 over pi squared. There we go. That's it. So congratulations, we went through the exam. So please do let me know how you did. I'm probably going to do some more practice exams for you. So if you enjoyed this or found it useful, please let me know, because it is a lot of work to put these exams together. So let me know if this is worth it at all. And yeah, let me know how you did in the comment. Make sure to join me and the community on Discord. We're building a community with people who are trying to learn physics in college or also in graduate level. So if you're interested, go to the description or the first comment where you can find the link. I'm also streaming on Twitch every now and then. The link is also in the description. If you want to support me, consider going to Patreon. I also have the link in the description. Every link is there. And if you want me to cover a particular topic that you are interested in, you can go to Ablebees. The link is up here and also again in the description. And there you can either start or support a petition, and that way I can try to cover some things that you may need, or a particular thing that you may need. So yeah, thank you very much for watching, and I'll see you in another video.